lead engineer, and Ken Smith, engineer at the Moore Canyon Bridge project. Also part of the team are Andreas Girder from EDI, who provided external checking for the project, Derek Kelly, Stoyanov from RWDI, who conducted the wind tunnel testing and bottoming analysis, as well as Gail Menelik, Andrew Grisik, Mark Stunenberg from Buckland Taylor, who were the client's reviewer. The main topics we'll be discussing today are the challenges involved in the design and construction of an Under-Slung cable bridge. These challenges include the derivation of the main cable shape and length, the construction sequence of the semi-rigid structure, the girder launch itself, and the dynamic response of the bridge under wind and live load. Do you have a question?
Hello.
The owner of the bridge are the Glory Creek Mining Corporation. Okay, actually, we'll answer that question at the end. Okay. Before we start on details, let me give you a brief description on the background of the project. The Moore Canyon Bridge is a part of the Glory Creek Mining Project located near northern BC, near Bachwin and Stewart. It's part of a mining road that will service the Glory Creek mine. The Moore Canyon Bridge will span an 80-meter deep canyon. It's a 200-meter clear span underslung cable bridge. Apart from the geographic of the site, the project's complicated by high winds, which are funneled down the canyon, heavy snow accumulation during winter, and a steep mountain rock face. The underslung cable bridge concept originated from Dragon Mikage. It gave an elegant solution to a unique challenge. The geography of the canyon make any work on the side of the canyon slope extremely dangerous and costly. In addition to that, the rock located lower in the canyon are unreliable. Now, this meant that any work to be done would preferably be limited to the top of the canyon. The underslung cable design satisfies the criteria. The bridge is to be constructed at the top of the canyon with skylines and the marine girder to be launched onto the semi-stiff structure composed of the main cable and the launch girders. Now, due to the nature of the design, the bridge requires unique construction sequence and could potentially be sensitive to wind and live load. Because of these concerns, a comprehensive study of the dynamic response of the bridge was completed during the design process, resulting in a design that greatly exceeds a scope that's typical of a 30% design. Now, the bridge is composed of two 2.5-meter deep composite main girders supported by vertical struts at 20-meter intervals. The main cable system consists of two groups of four 105-millimeter diameter cables. Now, these groups of cables sit 14 meters apart and are cross-braced with 35-millimeter diameter cables to provide a strong lateral truss system. In addition, there's two 75-millimeter diameter wing cables at the elevation of the girder. Let's have a closer look at the roadway details. Here we have the composite main girders supported by vertical struts at 20-meter intervals. The main girder sits on top of the launch girders. We'll later see how the launch girders will first be erected to create a semi-rigid structure as a base platform for the main girder to be launched over. The height of these vertical struts varies from 4.7 meters nearest to the abutment to 17.3 meters at the midspan of the structure. At the bottom, we have the struts sitting on the base strut units, which are clamped to the main cable system. Here we can see the rendering of the a strut and clamp system, as well as the cross-bracing cables. The cross-bracing cables are both over and under the main cable system. Now this ensures that all resultant forces will go through a common work point in the system. Initially, the strut beam was designed to be hung from the main cables. You will see that in most of our model studies. This design was later changed in favor of having the struts sitting on top of the main girders. A key component of the Moore Canyon Bridge project was the implementation of MIDAS as the primary analysis software. MIDAS excels in the analysis of cable structure with an accurate ability to model the nonlinear behavior of the cable stays. With the shape and strength length of the cable highly dependent on the weight of the bridge, an accurate counting of the bridge elements and their weights were established early in the project. And we wanted to use the suspension bridge analysis control in MIDAS to derive the main cable length, shape, and tension in the final condition. Now, an obvious difference between the Under-Slung cable system and the suspension system is that the tension forces in the hangers are compression forces, in our case, in the struts. Other major differences also include the absence of backspans and the towers. Well, due to these differences, or just our input error, the suspension bridge analysis control was initially unable to compute the shape and tension in the cable based on the underslung arrangement like you see here. So what we did was that we created a suspension model based on our dimension, as you can see here, along with the calculated dead loads applied along the bridge. We ran the suspension bridge control, and sure enough, it gave us the shape of the cable and the initial stresses. We then took the cables, deleted the suspension elements around it, and surgically connected the cable to our structural system, as you can see here. Now these establishes the first iteration of the forces in the main cable. They include the equilibrium element nodal table, the initial force for geometric stiffness table, and the initial force table. You can find a tutorial from MIDAS on how these tables are produced. With the use of the suspension bridge analysis control to determine the control geometry of the bridge, is therefore established under a idealized suspension system, where the deck and the main girder is only used to account for the weight and not for the stiffness. So having established the initial forces and the shape, we introduced the data into the construction model. The basic boundary setup of the construction model is shown here. We have pin support at the end of the cable where it's anchored in rock anchors, and roller supports at the end of girders. Also roller supports to simulate the saddle over the abutment back walls. Here you can see a rendering of the saddle structure. The strut frames are hinged at the top where they're connected to the bottom of the launch girders. And the launch girders are hinged at their end, so they're simply supported spanning between strut frames. And let's have a closer look at the cross-section of the bridge. As mentioned before, earlier version of the bottom strut beam design, the bottom strut frame is to be hanging from the main cables. This makes for easy construction because the bottom strut beams will naturally want to hang plumb, making installation with the strut frames easier. But the hanging pendulum effect will lead to no convergence in the model due to the fact that there's too many degrees of freedom in the system. We get around this problem by using the elastic link between the cable and the bottom strut unit and adding torsional stiffness in this link. We used a single line element to represent the group of 4 main cables at each side of the bridge. This element is located at the geometric centroid of the cable group. We also used a single line element to represent the two composite main girders. This was done in order to properly capture the torsional stiffness of the box that's created by the main girder and its lateral bracing system. The torsional stiffness of the box cannot be captured by simple line elements laced together by bracing members. The torsional stiffness of the main girder system was captured by creating a separate model, modeling the girder and the deck using shell elements laced together with lateral bracing elements, then applying a unit torque at the end of the box, which induces the rotation. The rotational constant of the box is then computed using the following formula. J equals TL over theta G, where J is the torsional constant, T is the unit torque that is applied, L is the distance from the rotational fixity, theta is the angle of rotation, and G is the shear modulus. This torsional stiffness was particularly important for this project because of the dynamic effect of the wind and live load, which we'll later go into with more detail. Now, the Moore Canyon Bridge was designed with its construction sequence in mind. The construction concept also originated from Dragon Markage. This cable, Struts, and launch girders would be constructed using skylines, and the main girders would be launched from the abutment. Now, let's have a step-by-step look at the construction sequence. It all starts with the construction of the abutments. Groups of 15 9 by 15.9 millimeter diameter strand anchors are embedded 18 meters deep into sound rock. These will provide an anchorage for the main cables. 105 millimeter diameter main cables are laid into position one by one. Now, the initial position of the cable is approximately 1.2 meters higher than its final position due to the lack of dead load at the initial stage. Additional dead loads come at a later stage will induce tension in cable, hence elongating it. Catwalks made of timber and welded wire mesh will be installed along the two groups of main cables, creating a 1.8 meter wide work platform along the two sides of the bridge. The bottom strut beam, along with cable bracing, are installed bay by bay to create a strong lateral truss system and a base platform for future work to be built on. The exact location of the bottom strut beam will be marked on the cable prior to shipment. This is done because the length of the cable will change depending on the construction stage, as well as the elevation of the cable will change. Preloads of approximately 8 tons will be hung at each end of the strut beam. The preloads apply additional weight to the system. They stretch the main cable, making them stiffer, and also it closes the gap between the final stage elevation and the current stage elevation. Now, this elevation change is required due to the rotational tolerance on the members to come. Keep in mind that each joint installed at the construction stage will need to allow for rotation due to the constant changing of the geometry of the bridge. The preloads may either be bags of sand, lock block, or water. With these preloads, we can create favorable geometry for future construction stages by adding or removing preloads at certain locations in order to raise or lower the position of bay lines. The strut frames, as well as the launch girders, are installed bay by bay, starting from bay line 10. And the launch girders are installed with a hinge at each bay line so that the system is flexible. The launch girder and the strut frame are to be lifted at once along with their bracing system. The free end of the launch girder is pin connected to the adjacent launch girder. The system is then slowly lowered onto the bottom strut beam with turfers to ensure that it's in line with the bottom strut beam. The angle at the top hinge at each stage of construction is checked through modeling to ensure that no clashes occur. Cable saddles have a radius on them. By checking and keeping the cable within that radius, we ensure that no excessive stress is applied on the cable during the construction stage. And wind load at the construction stage is particularly a big concern due to the fact that a significant amount of weight and surface area is added to the structural system, whereas the lateral system of the launch girder cross-bracing is incomplete until the last segment of the launch girder is installed. So during the wind event, the launch girder is essentially cantilevering from the fixed support that is from the west abutment. At this construction stage where the launch girder can experience the largest deflection, in order to reduce this deflection, wind cables are introduced into the system. Here we can see some lateral deflection results produced in Midas at the stage of construction, where the strut and the launch girders are constructed just past the midpoint of the bridge and also just before reaching the east abutment of the bridge. You can see that the lateral deflection at the top of the truss reaches up to 740 millimeter in the most severe case, and also see how the cable and the strut system rotate to accommodate for this movement at the top due to the difference in stiffness of the completed main cable system and the incomplete launch girder system. Next, the wing cables are installed, strengthening the lateral bracing system at the girder level prior to the main girder launch. Now that the launch girder is complete with its lateral bracing system, it will become a launch platform along with the main cable system. To simplify each of the models that we're working with, the construction stage model was broken down into 3 models: the pre-girder launch model, the girder launch model, and the post-girder launch model, which also includes the post-CS analysis of the bridge. So let's have a step-by-step look at the deflection of the structure in Midas. The tuning of the preload arrangement through the construction stage had yet to be refined at this point of the analysis. Right now, all preloads are present at the stage after the installation of the strut beam to the end of the girder launch. Some preliminary studies have been completed looking at the difference with or without preload. You can see here from the deflection graph at each quarter of the bridge throughout the construction stage with or without the preloads. The vertical axis is the magnitude of deflection. The horizontal axis is the step-by-step construction stage. We can see here that the bridge experiences a significantly larger range of motion between the construction stage without the preload. The main girders are assembled in 20-meter segments at the east abutment and incrementally launched into its position on bridge. The launch will be facilitated by launch sliders with greased Teflon surface, like you can see here, and launch guiders, as you can see here. Now, there's a number of variables, challenges, and solutions to this procedure. The flexibility of the semi-rigid system composed of the main cable and the launch girders will deflect significantly during the girder launch. This soft platform creates a challenge since it means that the support condition and the elevation and stiffness will be constantly changing. But several solutions have been utilized in order to overcome these challenges. A hydraulic controlled launch nose capable of being raised and lowered to match the contour of the launch platform is introduced. A pin connection. It's a hinge connection between the first and second first and second segment of the main girder, as well as the last and second last segments. These hinges create a flexibility in the main girder system. This is important because the difference in stiffness between the main girder and the launch platform. A stiff main girder and a soft launch platform can create an unpredictable support condition. Dangerous conditions can exist in main girder if they lift off between supports. This can increase the stresses in main girder significantly. Now, there's also the possibility of using the flexibility of the launch platform to our advantage. By rearranging preloads, we can raise and lower the platform contours to counter the deflected shape to create favorable conditions. Studies have been conducted between the main girder with or without launch hinge. Here you can see here that the bending moment in the main girder is significantly reduced due to the introduction of the launch girder hinge. Here we can see the positive moment that's reduced at the front, and here we can see the negative moment that's reduced at the rear. You can see here that the launch hinge utilizes the full splice connection bolt holes to provide a temporary hinge. At the end of the launch, the hinge will be closed by tightening the top and the bottom clamp rods, then installing the full moment splice. Now let's have a look at the step-by-step deflection in Midas throughout the bridge launch. Here we can see the deflection of key locations in the bridge throughout the launch. The graph we have here represents the deflection of the launch girder and main girder at the main girder tip, as well as the launch girder at the launch nose tip. Where these deflection meets, that means there's a clash in the system between the elements. And then future launch models can be revised to resolve this clash. Here we can see graph deflection, quarter points of the bridge, and how they behave with and without preload during the girder launch. Again, the vertical axis here represents deflection. The horizontal axis here represents the step-by-step construction stage. You can see, in general, the change in deflection between stages is much gentler with the preloads. The tension in the main cables gradually increase throughout the construction stage. Here we can see the graph of main cable forces at each construction stage as load is added. The vertical axis here we have the tension force in the cable. The horizontal axis here we have the step-by-step construction stage, as well as some post-construction stages load cases. These are ice load and snow loads. The deflection of the main cable changes throughout the construction stage. Here we have the vertical axis representing the elevation of the cable comparison to the control geometry. The horizontal axis is the bayline of the bridge, the length of the bridge. The deflection 0 is targeted at the end of the construction stage, and we can see that the main cable, when it's first erected, it's approximately 1.2 meters higher than its final condition. Now, the dynamic behavior of the Moore Canyon Bridge was closely studied in the 30% design. Primary concerns involve the aerodynamic stability of the structural system. We wanted to look for and avoid instability such as flutter. It's a self-exciting aerodynamic instability that can involve large amplitudes of torsional motion and vertical motion as well as a coupled motion. Vortex shedding. This is a vibration that can cause a submersibility and fatigue life concern. And we also want to look for galloping, which is similar to the effect at the Tacoma Bridge. For this purpose, Derek Kelly and Stoyan Stoyanov from RWDI was acquired to conduct the wind tunnel study for the Moore Canyon Bridge. We're also concerned about the life load excitation of the bridge. Primarily, we want to investigate the appropriate dynamic load factor that should be applied. For this purpose, a rolling stock analysis was performed. Early in the design process, an eigenvalue analysis was conducted on the design. It's a model where we study the period of oscillation between various modes of vibration, with a particular focus on the first vertical mode and first torsional modes and the ratio between the two. The closer these two modes are together, the more likely dynamic effect such as flutter and galloping can occur. Therefore, you can understand that it's of particular importance that the torsional stiffness and behavior of the bridge was captured accurately. Part of the capturing the torsional stiffness was to model the bridge system with an accurate torsional stiffness composed of the box effect of the main girder system. Another part of the capturing the behavior was to be diligent in taking into account the polar moment of mass that existing in the elements, which don't contribute in stiffness, but contributes in mass. This is where the center of rigidity and the center of gravity is offset from one another. In our case, additional rotational mass was added along the center of the main girder. This is applied using the nodal mass function in Midas. Now let's have a look at some of the vibration modes that are created through Midas. We start with the crystal construction stage vibration. Here we have the first vertical mode. Here we have the first lateral mode. Here we have the second vertical mode and the first torsional mode. Now we look at some vibration mode for the completed structure. This is the first lateral mode. This is looking from the top and from the end. You can see that there's a little bit of rotation in the system as well. Here we have the first vertical mode, the second lateral mode, and the first torsional mode. Midas compiles the output of the eigenvalue analysis, and here we can see the frequency of each mode. As you can see here, the ratio between our first vertical mode and our first torsional mode is approximately 1.4. Ideally, you want to be in the range of 1.4 or higher. Then there's the mass participation table. These are all very useful information for us and the guys at RWDI. Now, RWDI was acquired to conduct the wind tunnel study of the Moore Canyon Bridge. The natural mode shape, frequency of the bridge, topographical data as well as meteorological data was provided for RWDI in order to conduct the topographical study, bifurcation analysis, as well as a sectional model test. A scale 1 to 3,000 topographical model of the Moore Canyon terrain was produced to study the effect of the canyon on the wind load at the location of the bridge. A scale 1 to 30 sectional model was created for a 60-meter segment of the bridge to study the aerodynamics stability of the bridge cross-section. The sectional model captures the characteristic height of the bridge, mass of the section, the first vertical, lateral, and torsional vibration mode of the bridge, and the vertical and torsional stiffness and dampening of the bridge was captured using air springs at the ends, which make up the end condition of the model. Here we can see the expert model in the wind tunnel. Variables in the wind tunnel testing includes a wind speed, angle of attack, vertical dampening and torsional dampening, as well as smoothness of turbulence in the airflow. The percentage of dampening in the structural system is a critical unknown to the study. The level of dampening can dramatically change the result of the test, but unfortunately, the dampening can only be accurately measured once the structure has been constructed. You can see that the motion is created by hand at the end of the bridge. We're just testing the stiffness of the bridge by hand. You can see that the bridge is quite torsionally stiff. Vortex shedding was discovered as an effect that can occur at a 1-year return period wind event. This does not create a critical load effect, but it can be uncomfortable for occupants. It's a serviceability issue. No flutter was detected, but galloping can occur under very low structural dampening, and but a slight increase in the structural dampening or increase in the turbulence in the airflow, the galloping can be suppressed. They have found that for the Moore Canyon Bridge, due to the effect of the canyon terrain, the local wind is likely to be very turbulent. Mass dampers and wind fairings has been recommended for the Moore Canyon Bridge in order to create a favorable response during the wind events. Here we can see some concepts of the wind masks that are applied over the mid portions of the bridge. The results of the RWDI study come in various wind load combinations. These combinations have been amplified by buffeting effect, which is a high frequency instability that can induce an impulse of load increase. 10 wind load cases were applied in the final model, but here we can see an example of one load cases that is applied. So the rolling stock analysis for the Moore Canyon Bridge was performed in Midas. For our bridge, we were concerned about the live load excitation, and this is associated with the dynamic load factor that's appropriate during the analysis of the bridge components. We studied the effect of the vehicle running at different speed, spacing, and eccentricity from center line of the road. The rolling stock analysis is a time history analysis with a forcing function of the moving vehicle. The forcing function represents the loading which is applied by the vehicle on a single load with respect to time. As you can see here, we have an example of the forcing function. On the vertical axis, we have the force applied. The magnitude is the force applied by each truck axis. The horizontal axis, we have time. The time spacing depends on the axle spacing of the truck, the distance between trucks, and the width of tire contact area that we assume. This forcing function will be applied on the node along the main girder. For our model, there are 801 nodes spaced at 0.25 meter spacing. This spacing is due to the tire width that was assumed for the analysis. Each node is set to run the forcing function at different start time. The start time is set that so the node would run the forcing function one after the other. This creates a wave effect that runs along the bridge, similar to a wave that you could create with a crowd of people. each going through the motion of standing up and sitting down, but doing that one after the other. You can imagine applying the forcing function on 801 nodes at different start time is a tedious task. So for this purpose, we created inputs like on a spreadsheet, like you see here, and utilize the MCT function of Midas. The MCT function is basically the analysis model that's displayed in lines of code instead of a graphical display. In this case, this was very helpful for us, where we could copy and paste lines of code from the spreadsheet into a text editor. Here we can see the rolling stock analysis in action in Midas. Now this is a graph produced from the results from Midas. The graph represents the effect of live load on the node that's 3/4 point down the bridge. The vertical axis represents magnitude of velocity, displacement, and acceleration in meters and seconds. The horizontal axis represents time in seconds. You can see here that the vehicle enters the bridge here, and the elevation of the node elevates as the cable tension increases. And as the vehicle approaches the node slowly deflects, and this is where the vehicle is at the 3/4 point of the bridge. And here is when the vehicle leaves the bridge. So overall, we find that the bridge is not very sensitive to live load citation. But that's not to say the surface of the bridge will be perfect and there won't be bumps on the road. Therefore, we still apply the dynamic load factor of 1.25 as recommended by the bridge code. Here we can see the bending moment diagram on the main girders as the truck travels across the bridge. You find that the girder experiences negative bending, tension on the bottom, where the truck is positioned. And everywhere else on the bridge, it's positive bending, which is tension on the top. This is due to the fact that the live load stretches the cable, and the cable straightening where less load is applied, pushing the strut frame upwards and producing negative bending in the main girders. Here we can see some D over C ratios that we produced for the various bridge components. And that's all I have for you today.